Okay, now we have a new question here. Let us see how we can approach it. It's also very simple. We have this and then this, but let us start with this one. The particle describes a simple harmonic motion in a straight line, and it starts from rest. And when it's 3 meters from the equilibrium position, it's traveling at the speed of that and accelerating at that. Find the angular speed. Now here, the question is telling us that it's accelerating, so they are giving us velocity. This is not maximum, it's just the velocity. And this is not maximum acceleration, just acceleration. So all those things, whenever they are giving them to you. So traveling at, so the velocity is 8 meters per second. They're also giving us acceleration at 12 meters per second. Okay. So they are giving us x. So whenever you are from the equilibrium, they are giving you x from the equilibrium position. That's the idea. So it means that now, the case we have, this is the case that we are having. So we won't be having this, we are having this. This is the equilibrium position. Let me call it O. So they are doing us that this one is 3 meters from O. So these are my 3 meters from O, the equilibrium position. Okay, so this is where it's starting at rest. Rest there. Okay. Now, to get the angular speed, I know that if I have velocity, I have the relations between the velocity. I have also the acceleration. I have the distance from. So if it's accelerating like that, it means that you know that the equation of acceleration, I think we all know, that always our acceleration is given by negative omega squared x. So if you take magnitude both sides, so magnitude of x is going to be negative x, which will be now our n is going to be squared x in that order. So they're giving us expression as 12 equaling 2. We want the angular, this is going to be 3. So from here, it's like our omega squared is going to be 4. And so our omega is going to be 2 rad per second. So this is our part A. Then part B, they want us to get the angular speed. So angular speed, how do we get the angular speed? You see here, they want us to get amplitude. Amplitude, you see I don't have amplitude, but they give us the velocity. We all know that. Oh, should I write here? Okay, let me write here. Know that our velocity always, velocity squared is equal to angular speed squared, then minus the displacement from the equilibrium position. They are giving us this. We have this, we want this, we have this. So, if we put into our formula, this is going to be 8 squared equaling 2. This one we got as 2 squared into, this is our amplitude. Then x, it's going to be 3 squared. So from there, we just simplify that. You see this one is going to be 16. This one is going to be 16 for the minus of 16. So this is going to be 9. When I take this side, I have my r squared. R is 25. So my r is going to be 5 meters. So this is the amplitude. So that's our amplitude. Then part C, let this be now part C. They're doing us that. Fine, so this time takes the particle to come back to the initial point, this initial point. Now, there, what I'm going to do, first of all, what I'm going to do, this is the idea that we are going to use. This is the initial point. Initial point. So this is our O, this is our end point. Now, from here, there are 3 meters from that side. So what the distance there? What do you think the distance is? So we can maybe get this distance, and then we need the time it takes from now. A complete cycle is when you come here, you go, you come back, then you come back here. So that's what we call a complete cycle. And the time taken to complete from here up to here is the period. So T equaling to 2 pi over W is time for a complete cycle. Complete cycle. Then let me say from here, okay, let me say that going from here, let me write it properly, from here, going up to there, to cover that distance here, let me call it T1. It means that also coming back to this point, when it's coming back, this is also going to be T1. Now, to get a time that requires this particle to move from here up to here, I'm going to get the whole time for the whole cycle, then minus the time I take to come here, then come back there. That's the time we are going to use to reach that point there. So from there, let us get our T1. So my x equaling to r cos t. Now, here we have, let me get the time to cover this distance 3. So I'm going to be having 3 equaling to, my amplitude is 5. It means that now, if the amplitude is 5, it means that from here up here it's 5. So this one is going to be 2 meters. Because the wall from here up to here is r. R equaling 5 meters. And always this is equaling to that. So here I'm going to be having now cos of 2t. I want to get this t. So from here I see now my time I'm going to use is T1. I'm going to use to cover there. So getting this now, so I have 3 over 5 equaling to cos 2t1. So if I simplify that, I'll be having now so let me show you here. Have a look. As you can see there, that's my answer. Now, because these are small angles, your calculator should be in the radians. These are small angles. So, you can see that 91 is 0.4636 seconds. So, the time that requires me to come from here up to here or from here up to there is all I. So that's 91. Now, the time for the complete cycle, we said it's going to be 2 pi over 2. And so from, okay, over, which would be 2 pi over 2. And so from there, my pi is 3.1416 seconds. So meaning that now the time to come back, so the time I want is going to be t minus 2t1, which is going to be, now 3.1416 minus twice 91, 0.436. So mean the time that it requires to come back to the initial position this is 4, 6, 36, 4, 6, 36. So I'm getting 2.2144 seconds. Means that now the particles from here to come back to this point is going to use 2.2144 seconds, and that's how we handle that question there. Okay, a particle is moving in a straight line described in simple. Now it's here, the moment you hear maximum, use now the equation for maximum. If you don't hear maximum, don't use them. So there's a difference between when they're giving you velocity, just acceleration, and then when they give you the maximum acceleration. Not that already. So here, so they're giving us maximum speed. I know that our solution for maximum speed is always given by Vmax is always given by R, and the angular velocity, and here they are giving us 5. Then they are giving us acceleration mass, is always given by R omega squared, which is 10. So they want us to calculate this particle, calculate the speed of the particle when it's 2 meters from the center of oscillation. 2 meters. Okay, if you have sketched that, this is my. Okay, so they are giving me, this is the part, so this is the center of oscillation. When it's 2 meters from, so meaning they are giving me this displacement here. So they are giving me x from there to here. So this one is going to be my x. So all I need, first of all, to get velocity now, we need first of all the omega, or the angular speed, and we did this also. So if I call this equation 1, I call this equation 2, I can then relate these two by dividing them. So 2 divided by 1, I have equaling to 10. Then I'll be having over RW over 5. So when you divide this and this, we have now our angular speed as 2 rad per second. Now if you have this, you can easily get our amplitude from there. So my R is equal to 5. That my R into 2 is equal to 5. Implying that now our amplitude is 2.5 meters. So I have the amplitude. Now I can easily get the velocity. Now my v squared x squared. So I need this. So my v squared will be this squared, 2 squared into r. R is 2.5. The whole squared minus x. The distance from the initial, from our equilibrium position. Our equilibrium position is always 4. This one is going to be 2 the whole square. And from there, so this is going to be times 4. That's going to give us 9. Then times 4, we are getting 9. Get the square root of both sides. Our b, this is velocity, so get the square root. It's going to be now 3. Now this is in meters per second. Whenever always they talk about velocity, always try to use this equation. If they talk about maximum velocity, this is the equation we have there. Maximum acceleration, as you see it there. So that's it. These two numbers we are going to see more. The next lesson, see you there.